All right, you guys. Okay, let's put it all together. So here's our last video on trig, and this is really showing you that the Pythagorean theorem actually works in every single triangle. So that's kind of the big idea here. So the big idea is we already knew from the past that we could use the Pythagorean theorem to determine whether something's a right triangle, right? That's this first one. But also it actually told us, the inequality here told us if a squared plus b squared was bigger than c squared, we knew it was an acute triangle, and the same for obtuse if the inequality pointed the other way. So actually, the values of a squared plus b squared and c squared, just comparing those would tell you what type of triangle it is. But mathematicians said, well, wait a second. So in other words, a squared plus b squared plus some extra value is equal to c squared. And in obtuse triangles, it's a squared plus b squared minus some extra value. So if only we could like numerically find that value, we could use the Pythagorean theorem in acute triangles and obtuse triangles. There's just some extra value that we didn't yet know. And that's what the law of cosines is. So really, it's just that the Pythagorean theorem does work in every single triangle if we just add that one more term to the equation, that one more little adjustment, okay? So the law of cosines is right here. It's c squared, so the hypotenuse, or in this case, it's any side, because it doesn't matter which way you orient your triangle. So any given side is equal to a squared plus b squared minus 2ab times the cosine of c. Now it just happens that in a right triangle, this term ends up being 0 because the cosine of 90 degrees is 0. So in a right triangle, this formula is a lot easier. This term goes away and we just have the classic a squared plus b squared equals c squared. However, if the angle is 60 degrees or 1 degree or 100 degrees, we could still use this formula now. We're going to derive it in just a second here. Okay, it works in every single triangle. So we're going to go ahead and do a little proof here. One little caveat is I'm not going to look at obtuse triangles because, again, in this specific year's class, we have not expanded trig functions using the unit circle to go beyond 0 to 90. We haven't looked at what a cosine of 100 degrees looks like yet. And since we haven't done that, I'm going to just avoid it for now. This proof does work in obtuse triangles as well, but we're just going to go ahead and start with an acute triangle. All right, so let's just start with a triangle like this, okay? All I did was label it with A, B, and C here. Again, if we are not yet able to do trig outside of a right triangle, the very first thing we should do is make a right triangle. So I'm going to just drop an altitude down here. I know it's perpendicular on both sides. I'm going to call this the height. And then I'm going to break up the bottom into some portion and the rest, right? So this A, I'm going to split into some portion here, and then the remainder, so a minus x, whatever's left over there, okay? So in the last one, what we did with the law of sines is we looked at, okay, let's take the sine of, and I'm going to erase this, but the sine of angle C is this over this. The sine of angle B is this over this, and then we use substitution. So we're going to approach it differently. No surprise here, the formula we're going to be using is Pythagorean theorem. So let's use Pythagorean theorem in these two triangles and see what we get, okay? So in the left triangle, we get x squared plus h squared equals b squared, okay? Now in the right triangle, what we get is a minus x squared plus h squared equals c squared, okay? So I don't want to have that height in there, just like we did with the law of sines. I'm going to use substitution with this system of equations to get rid of that h, okay? So I'm going to restate the first theorem as, or first equation as h squared equals, just subtracting x squared from both sides. The first one just becomes b squared minus x squared, okay? So that first equation, that's what it's going to become. Now I'm going to substitute that into the second equation. So now I'm combining the two, eliminating the variable h, and what we get here is, just restating the second equation, we get a minus x squared plus, and now I can substitute, right? I can take this value here, and since I know what h squared is equal to, I can just plug that right into h squared. And so instead of h squared, I'm going to put in b squared minus x squared there. Okay, going back to blue. And that's all equal to c squared. So now I've got one equation. All right, I'm going to just multiply this out here. What we end up getting is a squared. Now multiplying this out, we get minus 2ax, and then we get plus x squared plus b squared minus x squared equals c squared. Now look at that. The plus x squared and the minus x squared already just canceled out, okay? Well, that's really nice, okay? So the fact that these two are gone just made our life a little bit easier, okay? So now we've got a squared, I'm just reordering it, plus b squared minus 2ax equals c squared. We're already almost done, okay? The only problem here is we don't know what x is, right? I'm going to have to find that in every single triangle. That defeats the whole purpose. That's not a known quantity of the original triangle. So somehow I want to solve for x. Like, what is that in terms of a, b, c, and the known angles a, b, and c? Like, what is x? So I'm going to go back to that first right triangle there. And how could I express x? Well, in this right triangle, I don't know what portion of angle A is up top, but I do know angle C. And I do know side B. So what I could do is I could say, well, the cosine of angle C, and that's in this left-right triangle here formed by the altitude. So the cosine of angle C is equal to the adjacent side over the hypotenuse. And so just solving for x there, multiply both sides by b, I get that x is equal to b times the cosine of angle C. And now you can see where I'm going with this. I'm just going to take this and use it to substitute in here for x. And so what I get is a squared plus b squared minus 2a. And then I'm going to substitute in, instead of x, I'm going to put b cosine of c there. And that's all equal to c squared. And sure enough, we just arrived at the law of cosines, right? So that's the Pythagorean theorem with that extra little correction value. Now this has a lot of uses, and at the end of the video, I'll kind of summarize, if I'm given any triangle with some known values, what strategy should I use to know whether I'm using the law of sines or the law of cosines? But let's just jump into an example or two right now, okay? So here's a direct example. Notice that I cannot use the law of sines here, right? I would need a pair of side and angle, I don't have, side and angle, I don't have, and side and angle. I would have to have one of those known to be able to then use the law of sines to set it equal to something else, but I don't. Okay, so I can't use the law of sines here. Let's go ahead and use the law of cosines, okay? So I could label everything if that's helpful. So let's call this A, and I'm going to call this C and C. Whoa, that's not a C. And this one B and B. Okay, so what I want to do here is plug it into a squared plus b squared equals, minus 2ab cosine of c equals c squared. And I want to find the missing value of c here. Okay, so let's plug it in. So a squared, that's 41 squared, plus b squared, 36 squared, minus 2 times 41 times 36 times the cosine of angle C is 49 degrees equals c squared. And so that's just a numerical value. I will let you calculate that, but in the end, c will be equal to the square root of 41 squared plus 36 squared minus 2 times 41 times 36 times the cosine of 49. Okay, now just to reiterate a really simple algebra 1 mistake, that the square root at 41 squared plus 36 squared is not equal to it is not equal to the square root of 41 squared plus the square root of 36 squared. That is absolutely not possible. That horizontal line right here says you need to do everything under that horizontal line first, get that to be one numerical value, and then take the square root. You can't split that up. So I just want to point out that common mistake. Okay, separately over here, again, maybe labeling is helpful. So let's call this my angle C, this my A and my B. And so here's B, here's A, and here's C. Notice that, whoa, I got a circle for the first thing? That's crazy. Notice that I'm using C as the angle and the side that I'm trying to use to solve for one another, okay? In general, what we're really looking at here is A, B, C, and the right angle is like the angle C, except it's not a right angle right now. So all of our problems that we're looking at right now are like a side angle side where the angle is not 90 degrees. So that helps me think about it. I'm trying to solve a side angle side problem, and the angle is C, and I'm using the two legs A and B. You can structure it in any way you want, but that to me really helps solve that. Okay, so let's go back over here. Let's set up the equation. I've got a squared plus b squared minus 2ab cosine of c equals c squared. And there we go. You just plug that into a calculator, take the square root, and you're done, okay? Now let's do it in reverse, okay? Now you're given a side problem, okay? So now we want to use this equation to solve for an angle. So anytime we're trying to solve for an angle, that's going to end up being an inverse trig problem, right? We're eventually going to get to a point where we go, the cosine of angle, in this case A, is equal to 0.7. So what's the original angle? And then we use the inverse trig, saying, well, I know the output. What was the original angle that gave me that output? So that's going to be the end result here. So the last step will be inverse trig. But in the beginning, we just set it up like before. So I'm going to think about it as like a side angle side. I'm looking for this angle. So if it helps to label them, I'm going to call this my A and my B. This will be my angle C. So this will be my side C. I don't need to label the others, but I could. This would be angle A. This would be angle B. Okay, so here we go. My equation now is a squared plus b squared minus 2ab, and then times the cosine of, I don't know. I'm going to go ahead and call it angle A because that's what it is in this problem, but it's like the value of c in our equation, equals c squared. Okay, so that's our equation. Now we got to go ahead and solve to get to the bottom of this cosine of angle A. So to solve this, really what we've got here, if I just rewrite kind of a simpler version up here, what I see is like 5 plus, so number plus number minus number times x equals number. This is kind of the way I see it, right? We've got a number plus a number minus a number times cosine of c, and then all equals a number. So the very first thing I'm going to do is subtract this from both sides. I'm going to subtract this from both sides. And then once I have this negative 3x equals 0, then the last thing I'm going to do is divide by whatever number is in front of my x, right? So that's kind of the steps I'm going to follow. Now those were totally made up numbers. Don't think, where did Mr. Dilloughery just get those numbers? Those were made up. I'm just showing you this is analogously how I see the problem visually in terms of Algebra 1. I need to get rid of the two numbers first, with their own separate terms, and then afterwards I'm going to divide by whatever is being multiplied by x, okay? So here we go. I'm going to first subtract the 34 squared and the 36 squared from both sides. Whoops, 34 squared and 36 squared. So now my equation is minus 2 times 34 times 36 times the cosine of angle A equals, and on the right I've got 42 squared minus 34 squared minus 36 squared. Okay, so now I need to get rid of whatever is being multiplied by my cosine, right? So I want to get this by itself, and it's multiplied by this negative 2 times 34 times 36. So I'm going to divide both sides by that. I'm going to divide by this. Yes, you could compute this and make this a single number. I'm going to leave the calculations to you guys, okay? So we divide both sides by this, And now what we're left with is exactly what we wanted, right? So we've got now the cosine of angle A is equal to 42 squared minus 34 squared minus 36 squared all over negative 2, 34, 36. Okay, so anytime we've got that, and let's just go ahead and solve for this really quick, okay? So, nope, one more. Okay, so we've got 42 squared minus 34 squared minus 36 squared all over minus 2 times 34 times 36. Fingers crossed. Boom, there we go. So we get 0.281. This is rounded. We shouldn't round in the middle of our problem, but okay, so 0.281. So we've got cosine of angle A is around 0.281. And again, we shouldn't round in the middle, but that was all the number of digits my calculator gave me. Okay, so now rewriting that exact equation, that means the measure of angle A is equal to the arc cosine, or the cosine to the negative 1, of 0.281. Okay, so I'm going to go back over there. And I'm going to say, what is the arc cosine of 0.281? Boom, 73.68 degrees. So over here we get the measure of angle A is around, I have no idea what value we just got, 73.68. Okay, whoops. There we go. There we go. All right. So now back over here, and just to reiterate here, if you looked at this triangle in the beginning, you said, okay, these sides are all kind of close in values. So if I were to start with like 60, 60, 60 approximately, I would go, okay, well, this is the biggest angle. So let's up it to, I don't know, let's say 70 degrees. This is the medium, let's keep it around 60, and this is a little bit smaller, so let's make it around 50. So if I were to ballpark this, I would have said at the beginning, this angle's about 50, this one's about 60, and this one's about 70, just as a ballpark, and then we ended up getting about 73.68 degrees. So just so you can go back and check, yeah, that would be the biggest of the three angles. They're all pretty similar, just as a check, okay? Like in this problem, number 6, I immediately notice this is about a 3, 4, 5 triangle. So I'm guessing this is about a 90-degree angle, and that's what the problem's asking. So I'm guessing we're going to get something pretty close to 90. Maybe it's 93 or 87 or something like that. Okay, so let's go ahead and solve, okay? So again, it's the same as we had before. So we're looking for this angle C. So this is going to be a side A, side B, side C, and we're looking for this angle. So we get, this is going to be a lot of numbers. So 418 squared plus 328 squared, minus 2, 418, 328. Cosine of C, that's nice that it gave us that letter this time, equals 508 squared. Okay, so I subtract these two terms from both sides, and I get the negative still there. 2 times 418, 328, cosine of C equals, and then we get this big 508 squared minus 418 squared minus 328 squared. Okay, and then we divide by the coefficient here. So the coefficient of cosine C is this, so we divide that on both sides. And what we end up getting is the cosine of C is equal to 508 squared minus 418 squared minus 328 squared all over negative 2, 418, 328. And so what that means is the measure of angle C is equal to the arc cosine of, and then we just rewrite that entire term right there. And this way you just take the inverse cosine of that and get that. All right, so that's the direct applications of it. But now let's look at bigger picture why and when. And I'm going to come back and solve these word problems. Why and when would we use this, okay? So every single triangle congruent shortcut we looked at is listed here, right? AAA doesn't work, okay? We need at least one side length to determine any size. Otherwise, the triangle could be huge or tiny, and we have no idea. ASS and SSA don't work because it narrows it down from infinitely many triangles to two possibilities, right? There's two places that leg could lie. It could be an obtuse or an acute triangle. So ignoring those, okay, if we come across a problem that's a non-right triangle and we have enough information about it to find the missing sides and angles, that means it's one of these other congruent shortcuts, okay? So either it's AAS, ASA, SAA, or the other two SAS, SSS, okay? Well, if we have any two angles and a side, right? So that would be if we have any of these first three, then we use the law of sines, right? And the reason is if we have two angles in a triangle, we can just do 180 minus those two angles and get the third angle. So now you have all three angles in a triangle, right? So if I'm given, doesn't matter which two angles, which two sides. If this is 30 degrees and this is 75 degrees, I can always go, oh, beep, boop, bop, beep. The missing angle is, oh, 75. That was nice. And it doesn't matter now which side you have, okay? Let's say this one is 10. Well, now I can use the law of sines to say, okay, the ratio of sine of 75 to 10 is, well, that was crazy, then this missing side to the sine of 30. Right? So once you find all three angles, and if you have two angles, you can always get the third by subtraction, then you can use the law of sines. Right? But the times you can't use the law of sines is when you don't have a single, right? Like if you don't have a side across from an angle, you can't use the law of sines. That's when you use the law of cosines. So the law of cosines is when you have either SAS, so if you know, say this is 10, 15, and 30. Now that was the first type of problem we did today. You don't have a ratio this way. You don't have a ratio this way. You don't have a ratio this way. You cannot use the law of sines. That's when you fall back on the law of cosines. And similarly with SSS, let's say this is 5, 6, 7. You don't have a single angle across from a side where you could use the law of sines. Another way to think about this is you always know A and B in these two problems, right? You got two sides. Those are your A and B. What you're trying to do is use the third side to get the angle or the angle to get the third side. So either way, you're trying to use the big C to get the little c or vice versa because you know A and B every single time. So that's kind of when you would use the law of cosines is SAS or SSS. And then anytime you know two angles, right? As long as you have any side, so that's AAS, SAA, ASA. If you know the two angles, then just use the law of sines. It's easier, it's quicker. You don't have the whole Pythagorean theorem and square roots to deal with. All right, the last problems we'll do are just two word problems that you come across in this section. Okay, so it says two 24-centimeter radius of circle. So let's look. Here's a circle. It says we've got a radius of 24. We've got a radius of 24, and it says the angle between them is 126. Then what's the length of the chord connecting the ends? Okay, so we're going to connect the two ends. That makes a chord. And so this is just like an SAS problem, like the beginning, where we're going to have to use the law of cosines. Right? So in this case, I'm going to label this. That's A and B. Here's our angle C, and we want to find the side C. So I'm going to go 24, that's A squared, plus B squared, minus 2AB equal cosine of, and then that's 126, is all equal to, and then the C squared, and that's what we're looking for here. So this ends up being just arithmetic. I could switch over to my calculator, and we get 24 squared plus 24 squared minus 2 times 24 times 24 times the cosine of 126. And what's that equal to? Now let's square root all that. And we get 42.768. Nope, other way. So C is around 42.768. Was that my short-term memory? Oh, we lost it. That's okay. There we go. So that's the big idea here. Now you could have noticed, especially in an isosceles triangle, a lot of times it's easier to just go, well, if this is 24 and this is 24, I can split this, and I know I split the top angle. So its top angle ends up being 63 and 63. Then you can end up, because you split this using an altitude right down the middle, you could just use the 63 in the sine. You can go the sine of 63 degrees is equal to, let's call this x, equals opposite over hypotenuse. And so x equals 24 times the sine of 63. And then the whole base there is 2x. So all we got to do is multiply this by 2. So let's just double check that 48 times the sine of 63 gives us the same value. Because anytime you're dealing with an isosceles triangle, you can cut it in half. And it often allows you to skip the law of sines or law of cosines and directly use right triangle trig pretty easily. So let's look. 48 times the sine of 63. Boom, we got the exact same thing, 42.768, which is what we were hoping. Shoop, there we go. All right, so another problem here is find the measure of the smallest angle in a triangle whose sides are 4, 7, and 8. Okay, so let's just draw our little triangle here. So here's 4, 7, and 8. Now it says find the smallest angle. So we know the smallest angle is across from the smallest side, so it's looking for this angle right here. Okay, so then just labeling this will be A, B, big angle C, and little side C. And so now using our equation, we get A squared plus B squared minus 2AB cosine of, and sure, let's call it C, equals C squared. And so now we're going to solve. So I'm going to first subtract these from both sides. So we get negative, and why not multiply this out? Okay, so that's 56 times 2, so 112. So we get minus 112 cosine of C equals, and 4 squared minus 7 squared minus 8 squared. Okay, what's that? Let's do it. Okay, so 16 minus 49 minus 64. That's 16 minus 113, so negative 97. Okay, so then we get negative 112 cosine of C equals negative 97. We divide by that coefficient here, and we get the cosine of C equals negative 97 over negative 112. We're going to go ahead and say, well, the same way to write that, if we're going to solve for C, is the measure of angle C equals the arc cosine of, and now I can get rid of those two negatives, so that's 97 over 112, and so the measure of angle C equals arc cosine of 97 over, oh, I shouldn't have put that dash. It's probably going to read that dash funky. Oh, it worked. Okay, so we get, almost exactly 30. It probably said round it, so let's just round it to 30. So this is 30 degrees. Perfect. Well, I hope you enjoyed the video. Again, it's pretty amazing that the Pythagorean theorem works in every single triangle, scalene, obtuse, acute, right triangles, just that little correction factor. Hope you enjoyed it.